Welcome to Mechanics of Rest. For more than a century, physics has treated the speed of light as one of the hardest boundaries in nature. Not just a fast number, not just the speed of a beam crossing empty space, but a limit woven into time, distance, energy, and cause itself. Yet the strange thing is that the closer science looks at that boundary, the less simple it becomes. Particles approach it, but never pass it. Galaxies can seem to recede beyond it. Quantum particles can share correlations across distance. Equations can even describe things that live on the other side of it, though whether nature allows them is another matter. So what really happens beyond the speed of light depends on what is trying to cross it. Matter, information, space-time, mathematics, or imagination. If you enjoy long, calm journeys through science, history, and the mysteries that still sit at the edge of what we know, consider liking the video and subscribing. New stories are added regularly, and your support helps Mechanics of Rest keep building these long-form explorations. Also, let us know in the comments where you are listening from, and if there is a person, topic, story, discovery, civilization, or era you would like covered next. Leave it below. For now, the journey begins with the number itself, the speed that light carries through the universe, and the limit written into motion. Chapter 1. The limit written into motion. The number is exact now. 299,792,458 meters per second. It is no longer only a measurement that laboratories try to refine, though it began that way for human beings, as a difficult act of timing something almost too swift to catch. In modern physics, the speed of light in vacuum is built into the definition of the meter itself. Distance is measured through light, rather than light being merely measured through distance. Long before that exactness settled into the language of standards and instruments, light had seemed to belong to a different category from ordinary motion. A stone thrown across a field made its speed visible by crossing one patch of ground after another. A cart moved because a wheel turned, and the wheel announced its motion in dust, sound, and strain. Light did not offer itself so easily. It arrived before the hand could mark its travel, filled a room before the eye could separate its entrance from its presence, and made speed feel less like a gradual crossing than an immediate condition. Early measurements of light were therefore measurements against difficulty. Ole Rømer, in the 17th century, noticed that the eclipses of Jupiter's moon Io did not keep perfectly to the expected schedule when Earth was at different points in its orbit. The delay was not enormous by ordinary clocks, but it was enough to suggest that light took time to cross the changing distance between Jupiter and Earth. The observation did not give the modern value, and it did not yet make light into a foundation of space-time. It did something quieter and necessary first. It made light finite. Once light had a speed, it could enter the same world as other measured things. Armand Fizeau sent light through a rotating toothed wheel in 1849, letting the returning beam be blocked or admitted depending on how far the wheel had turned during the journey. Léon Foucault later improved the method with rotating mirrors, bringing the measurement closer to the value accepted today. These were not merely clever devices for catching a fast phenomenon. They were instruments that turned a nearly unreachable motion into a timing problem, a distance problem, and a matter of repeatable procedure. James Clerk Maxwell changed the meaning of the number. In the 1860s, while gathering the laws of electricity and magnetism into a single theory, he found that disturbances in an electromagnetic field should travel as waves at a speed determined by the electric and magnetic constants of space. That calculated speed lay close to the measured speed of light. The connection was not an ornamental similarity. It placed light inside electromagnetism, as though what entered the eye from a flame or a star belonged to the same family as the force around a magnet and the charge gathered in a wire. This gave light a new kind of authority. It was no longer only a visible thing crossing space. It was a wave in the electromagnetic field, and its speed came from the structure of that field. When Maxwell wrote that light seemed to be an electromagnetic disturbance propagated according to electromagnetic laws, the old separation between optics and field physics narrowed. A candle flame, a radio wave, and later an X-ray could be placed on one continuous spectrum, differing in wavelength and frequency rather than in their basic nature. In ordinary life, speed belongs to the object. A bird has one speed, a train another, a river another. Each speed can be added to another in a straightforward way. A person walking forward inside a moving carriage has their walking speed added to the carriage's motion, at least to a good approximation. This habit of addition is so familiar that it feels like reason itself. Motion appears to be made from smaller motions stacked together. Light resisted that habit. If light was an electromagnetic wave, then the old mechanics of moving sources and moving observers had to face a strange demand. A beam from a lamp on a moving train did not fit neatly into the same addition of speeds that worked for a thrown ball. The equations describing electromagnetism carried a fixed speed inside them, and that speed did not behave like the speed of a carriage wheel or a rifle shot. A conflict had begun to form between the physics of motion inherited from Newton and the physics of fields given shape by Maxwell. Albert Michelson and Edward Morley entered this tension through experiment. In 1887, their interferometer attempted to detect Earth's motion through the supposed luminiferous ether, the medium many physicists still believed light required in order to propagate. If Earth moved through such a medium, light should have taken slightly different times along different arms of the instrument, depending on their orientation through that ether wind. The expected shift did not appear. The instrument was sensitive, the idea was clear, and the absence of the predicted effect became one of the most important silences in 19th century physics. The ether did not vanish in a single moment. Scientific ideas with long histories rarely disappear as soon as one experiment refuses them. Lorentz and others tried to preserve the framework by proposing changes in length and time for moving bodies, mathematical adjustments that could explain why the expected ether drift remained hidden. These efforts were not failures of intelligence. They were signs of a field trying to save as much as possible, while the measured behavior of light pressed against the older architecture. A boundary was forming, but it was not yet understood as a boundary in the modern sense. It did not resemble a wall placed somewhere in space, with light on one side and forbidden motion on the other. It appeared first as a stubborn sameness in the equations and experiments. The speed connected to electromagnetic waves refused to become just another relative quantity. It held its value where ordinary intuition expected it to shift. That is why the speed of light became more than a speed. In later relativity, it would become the conversion factor between space and time, the invariant speed that every observer in uniform motion measures for light in vacuum. But even before Einstein gave the principle its clean form, the ingredients were already gathered. Finite light from astronomical timing, laboratory measurements from wheels and mirrors, electromagnetic theory from Maxwell, and the failed ether drift from Michelson and Morley. The number had been approached from the sky, from the laboratory bench, from field equations, and from the absence of an expected fringe shift. There is a physical stillness in a limit that cannot be reached by ordinary accumulation. Add more force to a cart, and it moves faster until friction and material weakness take their share. Add more fuel to a rocket, and the rocket may climb to greater speeds if its engines and mass allow it. Near the speed of light, that simple expectation changes its texture. The closer a massive object comes to the boundary, the more resistant the final difference becomes. Not because space turns hard like a surface, but because energy and motion no longer trade with one another in the old proportion. This is the first answer to the question of what lies beyond light speed. Before anything can be imagined beyond it, physics asks what is trying to cross. A photon does not accelerate up to light speed in the ordinary way. Light in vacuum travels at that speed because massless electromagnetic radiation belongs to that condition. Matter is different. A proton, a grain of dust, a spacecraft, a human body. Each carries rest mass, and rest mass changes the question entirely. To reach light speed, a massive object would require unlimited energy under special relativity. That sentence is often repeated so often that it can become flat, but its meaning is exact. The problem is not that engineers have not yet built a strong enough engine. The problem is not only heat, or fuel, or structural strain, though those would matter long before the boundary. The deeper issue is that the relation between energy and velocity changes as the object nears c. Each added amount of energy produces a smaller change in speed, while the object's relativistic momentum continues to grow. Particle accelerators show this more plainly than imagination can. Electrons, protons, and heavier particles can be driven to speeds extremely close to the speed of light, and their energies can be raised enormously. Yet the speed itself creeps closer to q rather than passing through it. The machine does not discover a final hidden gear. It confirms, turn after turn, that the boundary is built into the mathematics of massive motion. This makes the phrase beyond the speed of light more delicate than it first sounds. It can mean a massive object somehow moving faster than light through nearby space. It can mean a signal carrying information faster than light from one place to another. It can mean a mathematical object whose equations place it permanently above c. It can mean a distant galaxy whose separation from us increases faster than light because space itself is expanding. It can mean a shortcut through geometry, where the path becomes shorter rather than the traveler locally faster. Those meanings do not share the same physical status. Some are forbidden by established relativity. Some are allowed as appearances that carry no message. Some are mathematical constructions whose ingredients may not exist in usable form. Some belong to cosmology, where the expansion of space changes distances without giving any local object permission to outrun a nearby beam of light. The boundary remains, but its edges are not simple. For that reason, the story cannot begin with warp drives, tachyons, wormholes, or quantum entanglement. It begins with light as a measured speed and then as a structural constant. Every later speculation will return to this first fact. In local physics, the speed of light is not simply the fastest thing anyone has found. It is the speed that ties measurement, causality, and motion into one shared structure. Matter approaches it, clocks respond to it, signals are bounded by it, and the universe is described around it. Chapter 2: Einstein's Constant Speed. Albert Einstein came to the problem of light speed through a contradiction that had become too clean to ignore. Mechanics described motion through the old habits of addition and subtraction, where the velocity of one body could be combined with the velocity of another. Maxwell's equations described electromagnetic waves moving at a fixed speed, a speed that did not seem to ask permission from the motion of the source or the observer. The two descriptions both worked too well to be dismissed. Their disagreement made the speed of light feel less like a number waiting to be measured again, and more like a loose joint inside the structure of physics. In 1905, Einstein published the paper that gave special relativity its spare and durable form. He did not begin by adding more machinery to the ether, or by imagining a hidden medium that could preserve the old picture. He began with principles. The laws of physics should have the same form for observers moving uniformly relative to one another, and light in vacuum should be measured at the same speed by those observers, regardless of the motion of the source. From those two statements, ordinary time and ordinary length could no longer remain untouched. Before Einstein, Hendrik Lorentz had already developed transformations that altered measurements of length and time for moving systems. Henri Poincaré had seen deeply into the principle of relativity and the mathematical structure surrounding it. Their work mattered, and it belonged to the same changing landscape. Einstein's move was different in texture. He made the constancy of light speed a starting point of physical meaning, not only a mathematical device for saving older assumptions. Clock synchronization became one of the quiet centers of the change. To say that two events happened at the same time seems simple when the events occur beside one another. Across distance, simultaneity requires a procedure. Clocks must be compared, signals must travel, and the finite speed of light must be accounted for. Einstein placed this procedure at the foundation, treating time not as a universal background that all observers automatically shared, but as something measured through operations inside a moving frame. A railway platform and a moving train later became familiar teaching images for this problem. But the underlying point was not the train. The point was that observers in relative motion do not divide spacetime into shared slices of now. A pair of flashes that appear simultaneous in one frame may not appear simultaneous in another. Nothing has gone wrong with either observer's instruments. The disagreement follows from the requirement that each still measures light in vacuum at the same speed. Here, the speed of light begins to reshape time itself. If a light pulse leaves a source and moves outward, every inertial observer must account for the same value of c. The adjustment cannot come from the light slowing down for one observer and speeding up for another. It comes from the measured distances and times through which the light is described. Time stretches between frames. Length contracts along the direction of motion. Simultaneity loses its old universal form. The change is easiest to misunderstand when it is treated as illusion. Relativistic time is not a trick of perception, like a distorted reflection in glass. Moving clocks genuinely measure less elapsed time between certain events than clocks following another path. Moving rods are not merely seen at a different length because of a visual delay. Their measured length in a relatively moving frame follows from the geometry of spacetime and the procedures by which length is assigned. The observer is not being fooled. The observer is measuring from a different frame. This made the speed of light a constant of relation rather than a preference of light alone. It belonged to the way space and time were joined. A beam crossing a laboratory did not merely report the behavior of electromagnetic radiation. It also revealed how intervals were to be compared between moving observers. Once this became clear, faster than light motion no longer meant only an object moving at a very great speed. It meant an object or signal pressing against the system that kept measurements consistent. The old addition of velocities survived only as an approximation. At walking speeds, railway speeds, and even the speeds of many spacecraft, the difference between Newtonian addition and relativistic addition remains small enough to hide inside ordinary experience. A person walking inside a moving vehicle still appears, for practical purposes, to have their walking speed added to the vehicle's speed. Near light speed, that habit fails. Relativistic velocity addition prevents two sublight speeds from combining into a superlight one. This is one of the more patient features of relativity. It does not deny everyday intuition, where everyday intuition is useful. It lets the old rules remain as low-speed approximations, close enough for thrown stones, engines, winds, and rivers. Only when motion nears the scale of c does the deeper structure become visible. Classical mechanics is not thrown away so much as placed inside a larger condition. A clock carried near the boundary would not experience its own ticking as abnormal. Inside its own frame, a second remains a second, and local physics continues without strain. The difference appears when that clock is compared with another clock that has followed a different path through space-time. The comparison is where relativity speaks. Time is not damaged during motion. It is accumulated differently along different world lines. The word constant can sound small for what light speed does in this theory. It is constant, not because nature happens to keep one convenient speed unchanged, but because that value organizes the conversion between temporal and spatial measurement. When physicists write space-time intervals, c is the factor that lets time and distance enter the same geometry. The number carries units, but the role is structural. It tells measurement how to pass between seconds and meters. That structural role is what makes the speculative question so difficult. If something massive could be pushed through C, it would not be like a ship crossing from one side of a harbor entrance to another. It would require the object's path through spacetime to change category. Below C, world lines of massive bodies remain timelike. Light follows null paths. Faster-than-light paths would be spacelike, and spacelike separation is not ordered in time the same way for all observers. The boundary is therefore not only mechanical, it is geometrical. Einstein's 1905 paper did not answer every later question. It did not contain general relativity, expanding space, quantum entanglement, wormholes, or warp metrics. Those belong to later chapters in physics. Yet the 1905 structure placed a guardrail around all of them. Any later claim about exceeding light speed would have to say exactly what was moving, what frame was measuring it, whether information was carried, and whether cause and effect remained consistently ordered. This is why the constant speed of light remains calm but severe. It permits photons to move as photons do. It permits massive bodies to approach, with growing energy and changing time. It permits observers to disagree about simultaneity while agreeing on deeper spacetime intervals. What it does not permit, within special relativity, is the simple crossing imagined by ordinary speed. The closer the question is examined, the less it resembles a race. A century after Einstein's paper, the boundary still stands at the entrance to every serious discussion of faster-than-light motion. The mathematics around it has grown, and physics has found cases where appearances become subtle, expanding cosmic distances, quantum correlations, phase velocities, and curved geometries that shorten paths. But the first lesson remains local and exact. Light speed is not merely a property of light. It is the rule that forces space and time to share one structure, and any object that tries to move beyond it must first pass through that structure. Chapter 3: The Energy That Has No Ceiling. Relativity becomes most visible when a machine tries to turn energy into speed. At low velocities, the exchange feels simple enough. More fuel, more force, more acceleration, and the moving body answers by crossing distance faster than before. A thrown stone, a rolling wheel, a falling weight, and a launched shell all belong to the older intuition in which speed can keep being added as long as a stronger push is supplied. Near light speed, that exchange changes. The added energy does not vanish, and it does not fail to enter the moving object. It enters as relativistic energy and momentum, changing the object's measured behavior in a way ordinary motion had hidden. The object can be driven closer to C, but every further approach becomes more expensive. The final gap does not close under any finite supply of energy. This is the reason the speed of light is not an engineering challenge in the usual sense. A bridge may fail because the material is weak. An engine may fail because fuel runs out. A rocket may fail because its mass grows too costly to lift. These are practical limits, and practical limits can sometimes be delayed by better materials. better design, or a more careful use of stored energy. The light speed boundary is different because it is not waiting for a stronger machine to arrive. A massive particle carries rest mass, and rest mass gives the particle a kind of membership in the slower-than-light world. It may move at rest in one frame. It may be accelerated in another. It may pass through a detector at almost the speed of light. Yet its path through space-time remains time-like, not null. And that distinction remains even when the particle's speed becomes extremely close to c. The language is mathematical, but the consequence is practical inside every accelerator built to test matter at high energy. In a particle accelerator, the boundary is not philosophical. It is tuned, measured, corrected, and encountered through hardware. Charged particles move through electric fields that increase their energy, while magnetic fields bend and guide their paths. At low energies, an increase in energy visibly increases their speed. At high energies, the speed changes less and less, even while the particle's energy rises by enormous factors. The beam does not cross the final line. It becomes more energetic while remaining below it. Synchrotrons make this especially plain. As particles gain energy, the magnetic fields that hold them on a circular path must be adjusted, because the particle's relativistic momentum has changed. The machine is designed around the fact that velocity alone is no longer the main sign of the particle's state. Energy, momentum, curvature, field strength, and timing must all be coordinated. The beam becomes a moving proof that speed is only one part of motion near c. Electrons reveal the effect with particular sharpness because they are light particles and can be brought near light speed with comparatively modest energies. Protons, much heavier, require greater energy to reach similar fractions of c, and modern proton accelerators push them into regimes where their speed is so close to light speed that ordinary language loses resolution. The difference between their actual speed and c may be tiny. Their energy, meanwhile, can keep climbing in ways that matter for collisions, particle creation, and the structure of the events recorded by detectors. This is why accelerator physicists do not speak about high-energy beams only in miles per hour or kilometers per second. Near the boundary, those units become almost misleading, because two beams may have speeds that differ by a very small fraction, while their energies differ immensely. The meaningful quantity becomes energy, often measured in electron volts and their larger multiples. A beam can be more powerful, more penetrating, more capable of producing new particles in collision, without being meaningfully faster in the everyday sense. There is a useful restraint in this fact. It prevents a simple fantasy from entering physics unnoticed. If speed alone were the only obstacle, then a sufficiently ambitious engine could be imagined as the answer. Relativity changes the problem before the engine is designed. It says that the closer massive matter comes to light speed, the more energy is required for a smaller gain in velocity, until the crossing itself would demand a quantity without limit. The relation can be felt as a surface that does not break, though no surface is present. Motion presses closer, and the response becomes less like passing through air and more like trying to smooth a grain that keeps revealing finer grain beneath the hand. Energy continues to enter the system, but the last difference between the particle and light does not behave like an ordinary distance. It is divisible without being exhausted. The closer the particle comes, the less ordinary closeness means. Cosmic rays provide a natural companion to accelerator beams. Some particles arriving from space carry energies far beyond what human machines can easily produce. And when they enter Earth's atmosphere, they create showers of secondary particles. Even then, the massive particles involved remain below light speed in local motion. Nature has built accelerators larger than laboratories, using magnetic fields, violent astrophysical environments, and long distances. But the same relativistic accounting follows the particles down into the atmosphere. The Large Hadron Collider gives a more controlled example. Protons inside it are guided around a ring about 27 kilometers in circumference, gaining energy before they meet in collisions inside detectors such as ATLAS and CMS. Their speeds lie extremely close to c, but the purpose of raising their energy is not to make them finally overtake light. The purpose is to concentrate enough energy into collisions for heavier and shorter-lived particles to appear, according to the rules that connect energy and mass. That connection is often remembered through Einstein's famous mass-energy relation. But in accelerator work, it is not a slogan. It is part of the working economy of the experiment. Energy placed into the motion and collision of particles can become the mass of newly produced particles, provided the conservation laws allow it. The detector does not watch matter break a speed rule. It watches energy become available for transformations that ordinary low-speed motion could never supply. Here, the boundary begins to show its double nature. It prevents massive matter from reaching c, but it does not prevent energy from accumulating. It blocks a certain kind of velocity while allowing other physical quantities to grow. The accelerator therefore becomes a patient machine for exploring what happens near the limit without crossing it. It does not defeat relativity by reaching high energy. It uses relativity so precisely that the machine would not work without it. The same pattern would confront any imagined spacecraft made of ordinary matter. Long before approaching light speed, the practical burdens would be severe: fuel, mass, shielding, heat, navigation, impacts from dust, and the enormous energy cost of acceleration and deceleration. Yet beneath all those practical problems lies the relativistic one. The ship has rest mass. Its occupants, structure, fuel, instruments, and stored information all belong to time-like paths. More energy could bring the ship closer to C, but not to Co itself. This does not make near-light travel meaningless. Quite the opposite. At speeds close to light, time dilation would become significant. Distances along the direction of travel would contract in the traveler's frame, and journeys that look long from one frame could be experienced differently from another. Relativity gives strange permissions near the boundary. It allows unequal aging, shortened measured distances, and enormous kinetic energy. It withholds the one permission ordinary imagination keeps asking for. A subtle point rests inside that refusal. The speed of light is not simply the speed of photons because photons are fast. Photons move at c because they are massless excitations of the electromagnetic field in vacuum. Massive particles, by contrast, do not become photons by being accelerated. Their identity does not dissolve into light at the boundary. The closer they are pushed, the more the energy relation marks their difference. This is also why almost light speed and light speed are not neighboring conditions in the ordinary sense. A particle may be brought to 90% of c, then 99%, then 99.999%, and the numbers can keep gathering nines. Each additional 9 has a cost. In principle, the sequence can continue without delivering equality. The arithmetic of closeness can make the boundary look near, while the physics keeps it unreachable for any massive object. So the question of what happens beyond light speed cannot be answered by imagining a stronger version of ordinary acceleration. Ordinary acceleration runs into a change in the meaning of energy itself. The boundary does not appear at the end of a long road, waiting to be crossed by something powerful enough. It is present in every step taken toward it, in the way energy is counted, in the way momentum grows, and in the way massive motion remains below sea. For this reason, later possibilities must find other routes if they are to remain even mathematically discussable. Tachyons would not be ordinary matter pushed past the limit. Wormholes would shorten geometry rather than accelerate locally through space. Warp metrics would move the structure of spacetime around a region rather than make a ship locally outrun a nearby beam of light. Cosmic expansion would change the distance between galaxies without sending a local object through space faster than c. Each idea begins by acknowledging what acceleration cannot do. The energy ceiling, then, is not really a ceiling on energy. Energy can keep being added. Particles can become more energetic. Beams can become more powerful. And collisions can open brief access to heavier forms of matter. The ceiling belongs to speed for massive objects. It is the place where added energy stops behaving like a simple promise of more velocity and begins instead to reveal the deeper structure that special relativity had placed beneath motion. Chapter 4. A clock near the boundary. A clock moving close to light speed does not feel broken from inside its own frame. Its mechanism continues according to the same local physics, whether the clock is an atomic clock, a vibrating crystal, a biological rhythm, or the decay time of an unstable particle. No hand feels heavy. No gear knows it is moving. The change appears only when that moving clock is compared with another clock that has taken a different path through space-time. This is one of relativity's gentlest but most unsettling consequences. Speed changes time, not by placing a visible strain on the object in motion, but by changing the amount of time accumulated along its path. A clock carried at high speed between two events measures less elapsed time than a clock that remains in a different state of motion between those same events. The difference is not a delay in observation. It is a difference in the actual proper time recorded by each clock. At ordinary speeds, the effect is too small to notice without precise instruments. A person walking across a room, a car moving along a road, and an aircraft crossing a continent all experience relativistic time dilation. But the amount is buried far beneath ordinary sensation. The human body cannot feel it. Mechanical clocks from earlier centuries could not reveal it. Atomic clocks, particle detectors, and high-speed particles finally made the difference measurable. A useful entrance into this effect comes from muons. Muons are unstable particles, heavier cousins of electrons, produced naturally when high-energy particles from space interact with atoms in Earth's upper atmosphere. At rest, a muon has a mean lifetime of about 2.2 microseconds. That is not long by human standards, and by ordinary low-speed reasoning, many muons created high above the ground should decay before reaching detectors near sea level. Yet many do reach the surface. Their arrival is not an exception to decay. It is one of the clean signatures of relativistic time. From the frame of observers on Earth, the muons are moving so quickly that their internal decay clocks are dilated, and they survive longer than they would if they were at rest in the laboratory. From the muon's own frame, its lifetime is normal. But the thickness of the atmosphere along its direction of travel is shortened. The same physical event has two descriptions, and both preserve the structure of relativity. This is not a decorative example. Cosmic ray muons became a practical demonstration that moving clocks accumulate time differently. Detectors placed at different altitudes record more muons than classical expectations would allow. The particle's brief lifetime, the height of the atmosphere, and the measured count at the surface form a small natural experiment repeated continuously above the ground. The sky supplies the particles. Relativity supplies the accounting. There is a rhythm hidden in this comparison. One clock remains with Earth. tied to the laboratory, the mountain, the detector, and the air through which the particles descend. Another clock belongs to the moving muon, carried inside the particle's own decay process. They are not ticking against a universal background that both must share in the same way. Their rhythms belong to different paths, and when the paths are compared, the difference has a measured size. The effect does not require particles from space. In the 20th century, atomic clocks became precise enough to make time dilation visible in machines built by human hands. The Hafeel-Keating experiment in 1971 carried cesium beam atomic clocks aboard commercial airliners flying eastward and westward around the world. When compared afterward with reference clocks at the United States Naval Observatory, the flown clocks showed time differences consistent with the combined effects of special relativity and general relativity. Motion mattered, and altitude mattered too. That experiment did not send anything close to light speed. Commercial aircraft move slowly compared with sea. Their usefulness lay elsewhere, in the precision of the clocks and in the care of comparison. Relativity was no longer only a theory for particles and astronomical measurements. It could be carried in a seat on an aircraft, brought back to the ground, and read in tiny disagreements between instruments designed to count time with extraordinary regularity. Modern satellite navigation depends on this kind of correction. Clocks aboard GPS satellites move relative to clocks on Earth and also sit higher in Earth's gravitational field. Special relativity makes the moving satellite clocks tick slightly slower than comparable clocks on the ground, while general relativity makes them tick faster because they are farther from Earth's gravitational mass. The net correction is built into the system. Without it, position calculations would drift. This is one of the quiet ways relativity lives inside ordinary technology. A phone finding its location is not thinking about Einstein, muons, or space-time intervals. It is receiving signals whose timing must be interpreted with relativistic corrections already folded into the machinery. The speed of light enters because distance is inferred from signal travel time. Clock behavior enters because the transmitters and receivers do not share the same motion or gravitational condition. Near the light speed boundary, these differences become much larger. A spacecraft moving at a significant fraction of c would still feel locally normal to those aboard it. But when compared with Earth, its clock would show less elapsed time. The travelers would not watch their own seconds slow. Their own speech, breathing, instruments, and chemical processes would remain internally consistent. The separation appears when the journey is compared with the time kept by those who did not share the same high-speed path. This is sometimes described as travel into the future, and the phrase is fair if handled carefully. A traveler moving close to light speed could return having aged less than people who remained behind. No causality has been broken. No message has been sent into the past. The traveler's world line has simply accumulated less proper time between departure and return than the world line of Earth. Relativity permits this asymmetry when the paths are not the same, especially when acceleration brings the traveler away and back. A near-light journey would therefore change the human meaning of distance. Stars that appear separated by many years of light travel from Earth could be approached differently in the traveler's frame because lengths along the direction of motion are contracted. To the traveler, the path can become shorter while the external universe ages more than the traveler does. This is not faster than light motion. It is the strange permission granted below the boundary, where time and length adjust so that local light speed remains unchanged. The distinction matters. Time dilation can let a massive traveler experience a long journey as shorter than observers at rest would expect, but it does not allow that traveler to outrun a light signal sent along the same route. If a beam of light leaves Earth at the same time as the spacecraft, the beam remains ahead locally. The spacecraft may experience less time, and the distance may be contracted in its own frame, but the local structure that keeps light at sea remains intact. In this way, relativity gives without yielding. It gives different elapsed times, different measured lengths, and different slices of simultaneity. It allows particles born high in the atmosphere to reach the ground, allows atomic clocks on aircraft to return with tiny differences, and requires satellites to carry time corrections inside navigation systems. Yet it does not open the simple crossing that faster-than-light imagination seeks. Everything happens beneath the same invariant speed. A clock near the boundary therefore answers the question in a different language from energy. Chapter 3 showed that added energy cannot push massive matter through C. The clock shows that even before the boundary is reached, time itself has begun to participate. Motion is no longer only a change of place. It becomes a different route through space-time, and every clock carried along that route keeps the record. Chapter 5: Signals, Causes, and the Shape of Before. A signal is more than a thing that moves. It is a claim that one event can influence another. A flash reaches an eye. A radio pulse reaches an antenna. A command reaches a machine. And in each case, the later event carries some trace of the earlier one. Physics does not treat that ordering as decoration. Cause comes before effect inside the structure of every usable message. Special relativity gives that ordering a geometry. Once light speed becomes invariant, events can no longer be arranged by a single universal time shared by every observer. Some pairs of events are close enough in spacetime that a signal moving at or below light speed can connect them. Others are separated in such a way that no ordinary signal, no particle with mass, and no beam of light can pass from one to the other in time. The distinction is not only a matter of distance, it is a matter of distance and time held together. Hermann Minkowski gave this structure its enduring language in 1908. Einstein's relativity had changed measurements of time and length, but Minkowski placed those changes inside a four-dimensional geometry. Space and time were no longer separate stages on which motion occurred. They formed space-time, and events occupied positions within it. What had seemed like strange effects of moving clocks and rods became features of a larger shape. Minkowski diagrams are simple drawings, but they carry a severe idea. A vertical direction may represent time, a horizontal direction space, and the path of light forms a boundary between what can be reached and what cannot. The future light cone of an event contains the events that light or slower signals can influence. The past light cone contains the events that could have influenced it. Outside those cones lie space-like separated events, too distant in space and too close in time for any light speed or slower connection. This is where faster-than-light motion becomes more than a question of velocity. If a signal could move outside the light cone, then it could connect events that relativity classifies as space-like separated. For one observer, the signal might seem to travel from event A to event B. For another observer in a different state of motion, the ordering of those space-like separated events could reverse. The same signal could then be described as arriving before it was sent. No paradox needs to be dramatized for the problem to appear. The trouble is already present in the geometry. Relativity does not give every observer the same division of distant events into simultaneous slices. It protects causal order for events that can be connected by light speed or slower influence. But it does not assign one fixed before and after order to all space-like separated pairs. Faster-than-light signaling would enter exactly that unprotected region. A corridor of possible influence opens from every event. It widens at the speed of light, not faster. Inside it, causes may travel outward through particles, fields, and radiation. Outside it, events may be arranged differently by different observers without contradiction, because no influence is supposed to cross that separation. The boundary is not visible in space, but it acts like a limit on the reach of consequence. A message that leaves the corridor would no longer belong to the same causal order. This is why the speed of light is also the speed of causality in known local physics. The phrase does not mean that light itself causes everything. It means that the maximum speed for transferring usable influence is the same invariant speed that light has in vacuum. Electromagnetic signals, gravitational changes, and any ordinary communication are bound by this structure. Information does not receive a separate permission to outrun the geometry that governs matter and fields. Relativity of simultaneity sharpens the issue. Two events that occur far apart may be simultaneous in one frame and not simultaneous in another. If nothing travels between them, the disagreement causes no physical trouble. It is a difference in how observers slice space-time. But if a faster-than-light signal is allowed between such events, then the disagreement can be used to create a loop in which a reply, sent in another frame, returns to the sender's past. The loop is not born from imagination. It follows from permitting signals into space-like regions. This is the deeper reason physicists are cautious with faster-than-light claims. A measured speed slightly greater than c would not only require a new engine or a new particle, it would require an explanation of how causal order survives. Either the theory would need a preferred frame, hidden beneath relativity's symmetry, or it would need a new rule preventing messages from being arranged into causal loops. Without such a rule, faster-than-light signaling would not merely expand travel. It would loosen the order in which events can depend on one another. A preferred frame is one possible escape, but it comes at a high price. Such a frame would restore a special standard of rest or a special ordering of time, allowing one frame to decide which event truly came first. The old ether had once played a role like that in 19th century thinking, though modern relativity removed the need for it. Bringing back a hidden preferred structure would not be impossible as a mathematical move, but it would have to explain why so many experiments continue to confirm Lorentz symmetry with great precision. The other escape is to allow apparent faster-than-light behavior while forbidding usable messages. Physics contains several examples where this distinction matters. A shadow can cross a distant wall faster than light, without carrying a local signal along the wall. A wave's phase can move faster than c, while the front that carries new information does not. Quantum entanglement can produce correlations across distance without letting either observer choose a message to send. These cases do not break causality because they do not transfer controllable influence outside the light cone. That distinction will matter again and again. Speed alone is not enough to define a violation. The question is whether information, energy, or causal influence is being transported. A pattern may move, a coordinate distance may grow, a mathematical phase may shift. Yet if no usable message travels from one event to another faster than light, the causal structure remains intact. Minkowski's geometry made this clarity possible. It turned causality into something that could be drawn, calculated, and classified. Tim-like paths belong to massive bodies and ordinary causal histories. Null paths belong to light and other massless influences. Space-like separations belong to events that cannot be connected by any signal obeying the light speed limit. The categories do not rest on human preference. They follow from the invariant interval between events. In this setting, the phrase beyond light speed begins to divide into separate questions. A massive object beyond c would have a space-like path, which ordinary matter cannot take under special relativity. A signal beyond c would threaten causal order unless some new rule prevented loops. A geometry that shortens the path might preserve local light speed while changing the larger route. Cosmic expansion would change the distance between galaxies without sending a local object space faster than c. The same phrase hides different physical claims. The simplest, faster-than-light fantasy treats speed as if it were only a number on a dial. Turn the dial high enough, and a ship reaches one star sooner than light would. Relativity changes the dial into a map of possible influence. The issue is not only whether the ship can move faster, it is whether the departure, arrival, and possible return signals can be placed in a consistent order for all observers who are allowed by the theory. This is why causality appears before tachyons, wormholes, or warp bubbles can be taken seriously. Those ideas must not only ask how something gets from one region to another, they must ask whether the resulting path lets effects precede their causes. Some speculative structures try to avoid the problem by changing geometry instead of local speed. Others accept unusual causal consequences and then search for constraints that might protect the universe from contradiction. None can ignore the light cone. A clock near the boundary showed that time changes with motion. The geometry of signals shows something sterner. Time is not only stretched or shortened along paths, its ordering across distant events depends on what kind of connection is allowed between them. Below light speed, that ordering remains protected where influence can truly travel. Beyond light speed, the protection weakens, and the question becomes not only where a signal goes, but whether the word before still means the same thing when it arrives. Chapter 6. Tachyons in the equations. Tachyons enter physics through a narrow doorway. They are not ordinary particles that have been accelerated too far, and they are not a hidden form of matter waiting just beyond the reach of a stronger engine. In the original speculative idea, a tachyon would already belong to the faster-than-light side of the boundary. It would never slow down to the speed of light from above, just as ordinary massive matter never accelerates up to it from below. The word itself comes from the Greek root for swift, and in the 20th century it became attached to one of the strangest possibilities permitted by certain mathematical forms. In 1967, Gerald Feinberg explored the idea of particles with imaginary mass, particles whose relation between energy and speed would be inverted compared with familiar matter. The proposal did not come from a laboratory detection. It came from asking what the equations of relativity might allow if one placed a different kind of mass term inside them. That distinction matters from the beginning. A mathematical allowance is not the same as a physical population of particles. Physics often contains structures that can be written down before nature decides whether they are realized. Some become real through experiment. Some become warnings about an unstable theory. Some survive only as names for a boundary that later work explains differently. Tachyons have spent their life mostly in that unsettled middle territory. For ordinary massive particles, added energy brings the particle closer to light speed without letting it reach c. For a hypothetical tachyon, the relation would turn strange. Adding energy would slow it towards c from above, while reducing its energy would make it move faster. Light speed would remain the forbidden boundary, but now it would be forbidden from the other side. The tachyon would not cross into ordinary slower-than-light motion any more than a proton crosses upward into light. The shape of that idea is slippery because it uses familiar words in unfamiliar positions. Speed remains speed, energy remains energy, and mass remains part of the discussion. Yet their ordinary relations no longer carry the same intuitive meaning. It is like finding a slope in a drawing where every step downward seems to carry the line higher. The graph can be drawn, the symbols can be followed, and still the physical object described by the drawing may have no place in the measured world. Feinberg's paper gave the idea a serious scientific name at a time when particle physics was already rich with new discoveries. The mid-20th century had filled detectors with particles that earlier generations had not imagined. Muons, pions, kaons, strange baryons, and eventually a deeper quark structure beneath the growing list. In that environment, the possibility of an unfamiliar particle did not sound automatically absurd. Nature had already shown that common sense was a poor catalogue of what could exist. Even so, tachyons were different from a new heavy particle appearing in a detector. A new particle below light speed could leave tracks, decay products, scattering patterns, and statistical signatures that fit into the causal structure of ordinary events. A tachyon, if it carried usable information faster than light, would press against the causal problems already described by Minkowski geometry. It would not only enlarge the particle zoo, it would ask whether cause and effect had a hidden arrangement deeper than special relativity seemed to allow. Searches and constraints followed the idea in different forms. Physicists looked for signs that known particles might behave as if they had tachyonic properties, especially in contexts where very small masses were difficult to measure directly. Neutrinos, because they are extremely light and elusive, became a recurring subject of such speculation. Yet careful measurements have not established tachyons as physical particles. The known neutrinos have mass, and the evidence places them within the slower-than-light side of the boundary. The term tachyon also changed meaning inside quantum field theory. In many fields, a tachyonic mass term does not usually mean that a real particle is racing faster than light through space. It often means that the assumed state of the field is unstable. The mathematics is telling the physicist that the system has been expanded around the wrong vacuum, and that the field wants to settle into a different configuration. Once the theory is described around the stable state, the apparent tachyon may disappear. This is a careful but important shift. The same word that once suggested faster-than-light particles can become a signpost for instability. A ball balanced at the top of a hill is not in a stable resting place, even if it can remain there in a perfectly drawn diagram. A small disturbance reveals that the chosen position was not the state the system preferred. In a field theory, a tachyonic term can play a similar diagnostic role, pointing not to superluminal travel, but to the need for a new ground state. The Higgs field offers a famous example of this kind of language, though it must be handled precisely. Before electroweak symmetry breaking is described around the stable vacuum, the mathematics includes a negative mass squared term in the Higgs potential. This does not mean that Higgs particles move faster than light. It means the symmetric state is unstable, and the field settles into a non-zero value throughout space. The particle observed later at CERN belongs to the stable description, not to a world of faster-than-light matter. String theory has also used tachyonic language in several settings. Some versions or configurations contain tachyonic modes that signal instability, and their disappearance can mark a transition toward a more stable arrangement. Again, the word is not evidence that an object has outrun light in a laboratory. It is a mathematical diagnosis inside a theoretical framework, useful because it tells the theory where it cannot remain as first written. There is a quiet lesson in this. Physics does not always keep words tied to their first imaginative picture. A term may begin as the name of a proposed particle and later become a technical marker for the shape of a calculation. Tachyon is one of those words. It carries the scent of faster-than-light travel in popular language, but in much professional usage, it often points toward instability rather than motion. Still, the original question remains tempting. If a real tachyon existed as a particle permanently above C, could it be used to send messages into the past? Under ordinary special relativity, the danger appears immediately. A controllable faster-than-light signal can be arranged, through different frames of motion, into a causal loop. Unless the tachyon obeyed some additional rule that prevented controllable communication, it would threaten the same ordering problem that light cones protect. Some theoretical discussions therefore separate existence from communication. A field might contain mathematical structures that look tachyonic without permitting a usable signal. An instability might resolve before anything travels from sender to receiver. A hypothetical particle might be impossible to control in the way a message requires. These distinctions matter because causality is not threatened by every strange mathematical speed. It is threatened by transferable influence that can be arranged outside the light cone. The measured universe has so far given no verified tachyon beam, no detector track requiring a permanently faster-than-light particle, and no communication channel that outruns light. That absence is not a proof that every future theory must use the same language, but it is a strong condition on speculation. A claim about tachyons must explain why they have not appeared in particle experiments, why they do not disrupt causality, and how they fit with the precision tests that continue to support Lorentz symmetry. This makes tachyons useful even without being observed. They mark one of the first places where the phrase beyond light speed becomes mathematically vivid and physically uncertain. They show that equations can sometimes be extended beyond the region where familiar matter lives. They also show that an extension of symbols is not yet an extension of nature. The boundary is not crossed merely because a variable is allowed to take an unusual form. In that sense, tachyons are less like a discovered country beyond light and more like a warning sign at the edge of a map. The sign does not say that nothing can be written there. It says that the writing must be read with care. Some marks may describe an impossible particle. Some may describe an unstable field. Some may describe a theory asking to be rearranged before it can speak about real objects. The next serious faster-than-light story would arrive not from speculative particles, but from a measurement that seemed, briefly, to show something already known, moving too fast. It would involve neutrinos, hundreds of kilometers of underground travel, and a timing difference measured in billionths of a second. For a short interval, the boundary around light speed appeared to tremble under the weight of an experiment. Then the instruments were examined more closely. Chapter 7. The neutrino that arrived too soon. In September 2011, a result from the OPERA experiment appeared to place a small crack in one of physics' strongest walls. Neutrinos sent from CERN, near Geneva, to the Gran Sasso National Laboratory in Italy seemed to arrive earlier than light would have crossed the same distance. The difference was tiny, about 60 nanoseconds across a baseline of roughly 730 kilometers. A human nervous system could never feel such an interval, but a precision timing system could record it, and the number was large enough to disturb the ordinary confidence surrounding the speed of light. Neutrinos were already suitable particles for unsettling expectations. They are electrically neutral, extremely light, and able to pass through enormous amounts of matter with little interaction. Billions of them cross the human body every second without leaving any ordinary trace. They are produced in nuclear reactions, particle decays, stellar cores, supernovae, and accelerator beams. Yet most of them pass through detectors as if the material world were almost transparent. Their difficulty makes every careful neutrino measurement an act of patience. The OPERA experiment had not been designed as a loose speculation about faster-than-light travel. It was built to study neutrino oscillation, the change of neutrinos from one flavor to another during flight. CERN produced a beam of muon neutrinos, aimed through Earth's crust toward Gran Sasso, where Opera waited underground. No tunnel carried the particles. They traveled directly through rock, interacting so rarely that only a small fraction could be detected at the far end. To measure their speed, physicists needed two things with unusual precision: the distance between the source and detector, and the time between emission and arrival. The distance was surveyed geodetically, tying laboratory positions to Earth-based reference frames. The timing depended on GPS synchronization, atomic clocks, and the careful accounting of delays in cables, electronics, and detector response. A faster-than-light claim is never only about the particle. It is also about every instrument asked to say when the particle left and when it arrived. The reported result was not a dramatic excess. The neutrinos were not minutes early, or seconds early, or even microseconds early. They appeared roughly 60 billionths of a second ahead of light's expected travel time. The scale was so small that it belonged to cable delays, clock synchronization, signal processing, and statistical reconstruction as much as to particle motion itself. In a measurement like that, physics and instrumentation become almost inseparable. A nanosecond is a thin piece of time. Light itself travels only about 30 centimeters in 1 nanosecond, a distance comparable to the length of a school ruler. Across 730 kilometers, 60 nanoseconds corresponds to a light travel distance of about 18 meters. The baseline between CERN and Gran Sasso stretched across countries and mountains, while the disputed interval could be translated into the length of a small room repeated a few times. Such measurements ask instruments to keep faith with details that ordinary experience would never separate. When the Opera collaboration announced the anomaly, the tone was cautious. The researchers did not claim that Einstein had been overturned. They presented a result they could not explain after months of checks and asked the wider community to examine it. That caution mattered. In science, a result that contradicts a central theory does not become true because it is interesting. It becomes a demand for repeated measurement, independent verification, and scrutiny of every assumption lying beneath the number. The broader physics community responded in exactly that spirit. Some theorists considered what faster-than-light neutrinos would imply, and the implications were severe. If neutrinos traveled faster than light by the reported amount, they should lose energy through processes analogous to Cherenkov radiation in vacuum, producing particle pairs and arriving at Gran Sasso with a distorted energy spectrum. Other observations, including neutrinos from supernova 1987A, also placed strong constraints on large deviations from light speed behavior. The anomaly had to fit not only one experiment, but the whole existing web of neutrino physics. Supernova 1987A had provided an earlier natural timing test. In February 1987, detectors on Earth recorded neutrinos from a supernova in the Large Magellanic Cloud a few hours before the visible light from the explosion became observable. That early neutrino arrival did not imply faster-than-light travel, because neutrinos escape the collapsing star's interior before light can pass through the surrounding stellar material. The important point was the long baseline. Across roughly 168,000 light-years, the neutrinos and later light remained close enough in arrival time to show that neutrinos did not exceed light speed by anything like the Opera reported fraction. This made the 2011 result more difficult to accept as particle behavior. A tiny timing excess over 730 kilometers would become enormous if the same rule applied across astronomical distances. Either the result had to depend on energy, environment, or some unfamiliar condition, or it had to be instrumental. The second possibility was less glamorous. but it sat closer to the habits of precision science. Instruments often know more ways to mislead than theories know how to survive. Gran Sasso itself gave the story a fitting physical setting without needing drama. The laboratory lies beneath the Gran Sasso mountain, shielded by rock from much of the background noise that would disturb delicate particle experiments. Opera used large detector structures built from layers of material capable of recording the rare interactions of neutrinos arriving from CERN. Most particles ignored the detector entirely. The few that interacted had to be reconstructed from traces left in matter. The timing chain was eventually examined with the kind of attention reserved for results that seemed too important to trust quickly. 2 instrumental issues were identified. One involved an optical fiber connection between a GPS receiver and the experiment's master clock, where a loose connection could introduce a delay. Another involved an oscillator used in timing. Together, the corrections removed the apparent faster-than-light result. The neutrinos had not crossed the boundary. The measurement system had carried hidden errors small enough to imitate a revolution. There is no shame in that outcome. It is one of the ways science remains attached to the world rather than to excitement. An experiment produced a surprising number. The collaboration exposed it to scrutiny. Other measurements followed, and the instrumental causes were found. The result did not become a discarded embarrassment so much as a documented case of how difficult it is to measure time across long distances at nanosecond precision. Later measurements from other Gran Sasso experiments, including Icarus, did not confirm superluminal neutrinos. The faster-than-light interpretation faded, and the ordinary relativistic boundary remained. Neutrinos continue to be strange in many ways. They oscillate, they have tiny masses, and they pass through matter with rare indifference. They did not need to outrun light in order to remain scientifically difficult. The opera episode also clarified the difference between humility and weakness in physics. A strong theory is not protected by refusing to look at anomalies. It is protected by letting anomalies come under measurement, repetition, and correction. Relativity survived the opera claim not because physicists declared it untouchable, but because the faster-than-light result failed the procedures required to replace it. This is important for every speculative question that follows. If a real faster-than-light particle or signal were found, it would not appear only as an isolated headline. It would have to fit timing systems, energy conservation, detector response, astrophysical constraints, and causal structure. Its existence would have to survive independent experiments. Its effects would need to appear where the theory says they should appear and remain absent where the theory says they should not. A single early arrival is not enough when the boundary being challenged holds together so many measurements. A tiny timing error can resemble a new universe when the measurement is precise enough. The opera neutrinos seemed to arrive too soon, but the smallness of the interval was also the clue. 60 nanoseconds belong to the world of electronics and synchronization as much as to the world of particles crossing Earth's crust. The correction returned the event to that practical world. Fiber connections, clock behavior, calibration, and the unglamorous discipline of checking the path of a signal through hardware. The story leaves the light speed boundary more clearly drawn. It shows that faster-than-light claims are not rejected by habit alone. They are given a chance to become real, but the chance is demanding. The claim must pass through the same instruments that first made it visible, and those instruments must be understood more carefully than the excitement surrounding the number. In this case, the neutrino did not arrive beyond light. The experiment arrived at a deeper knowledge of its own timing. After opera, the search for faster-than-light behavior did not disappear. It shifted back toward places where the apparent speed is not the same as a carried message. Shadows, wave crests, laser spots, And mathematical phases can all seem to exceed the light-speed boundary under the right conditions. They are gentler examples than superluminal neutrinos, but they are just as useful because they reveal how often the word speed needs to be handled with care. Chapter 8: Faster Shadows and Moving Patterns. Not every motion that outruns light is the motion of a thing. A shadow can sweep across a distant surface at a speed greater than c, while no piece of the shadow travels along that surface from one place to the next. A bright spot from a moving laser can cross the face of the moon faster than light if the angle changes quickly enough. Yet the photons that make the spot still travel from the laser to the lunar surface at light speed. The pattern moves sideways, the light does not. This distinction is one of the most useful protections against confusion. Physics asks not only how fast a mark, crest, or intersection appears to move, but whether matter, energy, or information is being transported with that apparent motion. A shadow has no substance to carry. A laser spot appearing first at one location and then another is made by different photons arriving at different places. The moving spot looks continuous to the eye or to a detector, but it is not a small object sliding across the surface. A long enough wall makes the effect easier to see in principle. Turn a lamp, and the edge of its shadow may move slowly across a nearby surface. Place the surface far away, and the same angular change corresponds to a much larger linear sweep. At great distance, the shadow edge can seem to cross the surface faster than light. No local signal has passed from one point on the wall to the next. Each point has only received or failed to receive light sent from the source. There is a quiet discipline in that explanation. It separates the motion of a condition from the motion of a carrier. The condition, brightness here and darkness there, can change in a sequence that looks like travel. The carrier, the light itself, still moves along its own path from source to surface. The apparent sideways speed is not the speed of a message running across the wall. Wave physics contains similar cases. A wave has crests, troughs, phases, envelopes, and fronts, and these do not always move with the same speed. Phase velocity describes the motion of a particular phase of the wave, such as one crest in a continuous pattern. Group velocity often describes the motion of the envelope that carries a packet of waves. Signal velocity concerns the arrival of new information. In ordinary cases, these speeds may stay close enough that the distinction remains hidden, but in dispersive media they can separate. In some media, phase velocity can exceed the speed of light in vacuum. This does not mean a photon or a message has been carried faster than c through the medium. The phase is a pattern within the wave, and patterns can move in ways that do not correspond to the transport of new information. The front of a signal, the first place where a genuinely new disturbance arrives, remains constrained by the causal structure of the medium and by relativity. Anomalous dispersion makes the subject more delicate. Experiments with carefully prepared light pulses have produced group velocities greater than c, and even negative group velocities, where the peak of a pulse appears to emerge from a medium earlier than simple intuition would expect. These experiments do not send usable information faster than light. They depend on the reshaping of the pulse by the medium, where the front and the information-bearing part remain causal. The peak is not always the message. A pulse moving through a dispersive material is less like a bead crossing a string and more like a shape being continuously remade. Different frequency components travel with different responses from the medium. The output pulse can form from the leading edge and internal structure of the incoming pulse so that the peak appears shifted. Nothing inside the material has to carry a new command faster than light. The medium has rearranged a shape whose earlier parts had already arrived. This kind of result is easy to overstate because the words are tempting. Faster than light sounds like a door opening. Negative velocity sounds like a reversal of ordinary motion. Yet, in these optical cases, the measured quantity is often a feature of a wave packet rather than a courier of new information. The distinction is technical, but it is the difference between a real violation of causality and a subtle behavior of waves. Radio astronomy gives another version of apparent superluminal motion. Some jets from active galactic nuclei can seem to move across the sky faster than light when observed from Earth. The effect appears when material moves close to light speed at a small angle toward the observer. Light emitted later has less extra distance to travel, so the motion projected on the sky can look superluminal. The source is not locally exceeding c. Geometry and light travel time have compressed the apparent motion. Such observations are not mistakes. They are predictable consequences of relativistic motion viewed from a particular angle. Astronomers use them to infer high velocities in jets from quasars and other active galaxies. The apparent excess becomes evidence of near-light motion and orientation, not evidence that matter has escaped relativity. A pattern on the sky can outrun the simple expectation, while the plasma in the jet remains below c. The same caution applies to rotating beams. A lighthouse beam or a pulsar beam can sweep across distant regions at an apparent transverse speed greater than light. If the illuminated surface is far enough away, the sweep is not a material object. It is a sequence of illumination events, each produced by radiation traveling from the source. No observer at one illuminated point can use the moving spot to send a chosen message instantly to the next point along the sweep. This turns the word speed into a family of meanings. There is the speed of a particle through local space. There is the speed of a signal carrying new information. There is the speed of a phase, the speed of a peak, the speed of a shadow edge, the speed of an illuminated spot, and the apparent speed of a projected motion across the sky. Some of these can exceed key without challenging relativity, because they do not perform the work that causality cares about. A useful test is to ask what can be controlled. If the faster-than-light feature cannot be used to choose a message at one location and deliver it to another outside the light cone, then the feature is not a superluminal communication channel. It may be visually real, mathematically real, and experimentally measurable, but it does not move information in the dangerous sense. Causality is not protected by forbidding every fast-looking pattern. It is protected by limiting transferable influence. The distinction may feel narrow, but much of modern physics depends on narrow distinctions. Mass and weight differ. Energy and power differ. Velocity and acceleration differ. Phase velocity and signal velocity differ too. When these words are kept separate, many apparent paradoxes lose their force. The world still behaves strangely, but the strangeness no longer says more than the measurement allows. This is why faster shadows and moving patterns belong in the story before quantum entanglement or wormholes. They teach restraint. They show that the sentence, "something moved faster than light," is incomplete until the something is named. A mark on a surface, a wave crest, a pulse peak, and a projected jet are not the same physical claim. Each must be asked whether it carries matter, energy, or usable information along the superluminal path. The light speed limit therefore survives many apparent exceptions, because the exceptions are not exceptions to the same rule. They occupy side passages in the language of motion. They make the boundary look more complex, not weaker. A shadow may cross a distant surface faster than c, but darkness is not a messenger. A phase may advance beyond the speed that ordinary intuition expects, but a phase is not automatically a signal. A jet may appear to outrun light across a telescope image, but the plasma follows a sublight path through spacetime. After these examples, the next question becomes harder because it seems to involve connection without ordinary travel at all. Quantum entanglement does not look like a shadow, a projection, or a wave peak. It links measurement outcomes across distance in a way that classical physics did not expect. Yet there too, the same discipline will return. Correlation is not the same as a message, and the speed of an influence is not always the right language for what the experiment has shown. Chapter 9. Entanglement without messages. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen described a difficulty that seemed to sit deep inside quantum mechanics. Their argument did not begin as a claim about faster-than-light communication. It began as a question about whether quantum theory could be complete. If two particles had once interacted and were then separated, quantum mechanics appeared to let the measurement of one particle tell something immediately about the other, even across great distance. Einstein disliked the implication. He wanted physics to preserve a stronger kind of local reality, where distant objects possessed their properties independently of measurement, and where no event here could instantly affect an event far away. The EPR paper made that discomfort precise. It suggested that either quantum mechanics was incomplete, or nature permitted correlations that did not fit the older picture of separable objects carrying fully settled properties through space. The word entanglement came from Erwin Schrödinger, who recognized that the issue was not an odd corner of the theory but one of its central features. Entangled particles cannot always be described as two separate systems with their own independent quantum states. The pair has to be described as a shared state, even when its parts are later found in different laboratories. Distance changes the arrangement of the experiment, but it does not restore the old separateness. This is where the faster-than-light temptation enters. If one particle is measured here and the other particle's correlated outcome is known there, it can sound as though something has crossed the distance instantly. The language of influence begins to press against the experiment. One side is measured, the other side is found in a matching or related state. The mind reaches for a signal moving between them because ordinary experience has few other tools for connection. Quantum mechanics does not make the situation so simple. The outcome of a single measurement is not controllable by the experimenter in the way a message must be controllable. A person measuring one particle cannot decide the result and thereby write a chosen signal into the other particle's result. The correlations appear only when records from both sides are later compared through ordinary slower-than-light communication. Before that comparison, each local sequence of outcomes looks random. John Bell changed the question in 1964. He found that the disagreement between quantum mechanics and local hidden variable theories could be turned into an experimental test. If particles carried predetermined local instructions, then their correlations would obey certain statistical limits. Quantum mechanics predicted violations of those limits. Bell's theorem made the old debate less philosophical and more measurable, which is one of the quieter turning points in 20th century physics. A Bell test requires pairs of particles, separated measurement stations, carefully chosen detector settings, and enough repeated trials to reveal the statistics. The result is not found in one dramatic pair of particles, it is found in the accumulated pattern. When the inequalities are violated, the pattern cannot be explained by the simplest local hidden variable picture. Nature does not behave like two sealed envelopes carrying pre-written answers from a shared source. Alain Aspect's experiments in the early 1980s gave strong evidence for this quantum prediction, and later experiments closed more of the possible loopholes. Detectors improved, random setting choices became faster and more carefully isolated, distances between measurement stations grew. By the 21st century, loophole-free Bell tests had shown with increasing precision that quantum correlations violate the limits expected from local hidden variables. The old classical picture had less and less room to stand. Still, the experiments did not create a faster-than-light telegraph. This point is essential. The violation of Bell inequalities shows that quantum correlations are not explainable by the simplest local realist models, but the correlations cannot be used to send a chosen message outside the light cone. The detector on one side produces outcomes that are locally random. The matching structure appears only when the two sets of results are brought together later by ordinary communication. The difference can be rendered through sound, though no sound travels between the particles. Two distant rooms may each contain a device producing a sequence that seems irregular when heard alone. Only after the recordings are placed side by side does the pattern between them become clear. Nothing in one room lets a listener choose the next note in the other. The relation belongs to the joint record, not to a controllable signal passing from one room to the next. This is why the no communication theorem matters. It formalizes the fact that quantum entanglement, by itself, cannot transmit usable information faster than light. Measurement on one part of an entangled system changes the description of the whole quantum state. but it does not give the distant observer a readable message on demand. Local statistics remain unchanged by the choice of measurement performed far away. The boundary around communication remains intact. The phrase "spooky action at a distance" is often attached to Einstein, and it captures his unease, but it can also mislead. It suggests a hidden shove crossing empty space, a private signal moving too quickly to see. Quantum theory is stranger than that picture and more restrained. It does not restore the classical world. It also does not hand the experimenter a faster-than-light switch. The ordinary idea of action may be the wrong object to carry into the quantum domain. Different interpretations of quantum mechanics describe the situation differently. Some emphasize the wave function as information about possible measurement outcomes. Some treat the wave function as physically real. Some allow non-local features in the underlying description while preserving the impossibility of faster-than-light signaling. Others distribute the meaning across branches, histories, or relational states. These interpretations disagree over what the mathematics says about reality, but the operational fact remains stable. Entanglement does not permit controlled superluminal communication. That operational stability is what keeps entanglement inside relativity's causal discipline. Experiments may be arranged so that the two measurements are space-like separated, meaning no light speed or slower signal can pass from one measurement event to the other in time. Yet neither side can use its measurement choice to send a readable instruction to the other. The correlations are real, but the channel is absent. Nature gives the pattern and withholds the message. This has practical consequences for quantum technologies. Quantum cryptography, quantum teleportation, and quantum computing all rely on entanglement in different ways, but none of them allow information to outrun light. Quantum teleportation, despite its name, requires a classical communication channel to complete the transfer of an unknown quantum state. That classical message is limited by C. The entangled resource is necessary, but it is not sufficient to move information instantly. The naming can make this difficult. Teleportation sounds like disappearance here and appearance there. Entanglement sounds like a hidden thread pulled across space. Collapse sounds like an event spreading instantly through the universe. Each word is a compromise between mathematics and human language. Used too loosely, the words begin to promise what the experiments do not provide. Used carefully, they point toward a world where correlation is deeper than classical physics expected, while communication remains bounded. There is a subtle kind of restraint in this arrangement. Quantum mechanics loosens separability without loosening causality in the ordinary operational sense. It permits correlations that appear impossible under older assumptions. But it does not permit an observer to send a chosen sentence into another laboratory faster than a beam of light. The mystery is therefore not smaller than popular accounts suggest. It is more exact. For the question of what happens beyond light speed, entanglement gives a strange answer. Something in the structure of quantum states does not respect distance in the classical way. Measurement outcomes across separated systems can be linked more strongly than local hidden variables allow. Yet the usable things humans care about in communication, instructions, warnings, commands, and records, still require ordinary signals to compare and interpret. The light cone remains the boundary of messages. This separates entanglement from tachyons, and from opera's neutrino anomaly. Tachyons would have been hypothetical faster-than-light particles if they existed in their original form. Opera appeared, briefly, to show known particles arriving too soon, until the timing system was corrected. Entanglement is neither of those. It is experimentally real, deeply non-classical, and still unable to carry a chosen message faster than light. The result is a universe less local than 19th century physics hoped, but not as permissive as faster-than-light travel would require. Correlation reaches where communication does not. A joint quantum state can bind the statistics of separated measurements, while each laboratory remains locally unable to read the distant choice as a message. The boundary has become more subtle, not less firm. After entanglement, the story moves from quantum connection to the scale of the universe itself. There, another apparent exception appears. Distant galaxies can recede from us faster than light, not because they are locally moving through space beyond c, but because the space between them and us changes with time. The next boundary is not inside a particle pair or a laboratory measurement. It is written into the expansion of distance itself. Chapter 10. Space itself does not keep the same rule. At very large distances, the question of speed begins to change its setting. A particle moving through a laboratory, a spacecraft crossing nearby space, and a light pulse passing between instruments all belong to local physics, where special relativity keeps the speed of light as the limit for matter, energy, and usable information. Cosmology adds a different kind of motion. Galaxies do not only move through space. The distance between galaxies can grow because space itself expands. This is not a small technical distinction. In local motion, one object passes through nearby space relative to another, and the rules of special relativity apply directly. A ship cannot overtake a light beam moving beside it. A proton cannot be accelerated through c. A signal cannot leave one event and arrive outside the light cone without raising the problem of causality. Cosmic expansion does not grant an exception to those local rules. It changes the background on which distant separations are measured. The idea entered modern science through general relativity. Einstein's 1915 theory did not treat gravity as a force acting across a fixed stage. It described gravity through the curvature of space-time, with matter and energy shaping geometry and geometry shaping the paths of matter and light. Once space-time itself became dynamic, the universe could no longer be assumed to sit inside an unchanging container. Space could bend, curve, stretch, and evolve under the equations. Alexander Friedmann found expanding and contracting universe solutions in the early 1920s. Georges Lemaitre later connected an expanding relativistic universe with astronomical observations, arguing that the recession of distant nebulae could be understood as the growth of space itself. Edwin Hubble's work in 1929 then gave the observation its lasting public form. More distant galaxies tended to show larger redshifts. The farther the galaxy, the more its light had been stretched toward longer wavelengths by the time it reached Earth. Redshift is the key sign in this story. In ordinary Doppler motion, a source moving away makes waves appear stretched, much as sound changes pitch when a vehicle passes and recedes. Cosmological redshift has a deeper meaning. The light does not merely leave a galaxy and travel through a static space while the galaxy moves away. During the light's journey, the scale of space changes and the wavelength of the light changes with it. The photon arrives carrying a record of expansion in the stretching of its own wave. This means that recession speed in cosmology is not the same thing as a local velocity measured by one object passing another. A distant galaxy can have a recession rate greater than the speed of light in terms of increasing proper distance, while every local observer near that galaxy still measures nearby light moving at c. Nothing in the galaxy's own neighborhood has broken special relativity. The superluminal recession belongs to the changing distance between far-separated regions of expanding spacetime. A sheet marked with points can give a partial mathematical picture, though the universe is not a rubber sheet and the galaxies are not ink dots in any literal sense. As the scale grows, the separation between distant marks increases. Marks farther apart gain distance from one another faster because more expanding interval lies between them. No mark has to crawl across the sheet at a forbidden local speed. The increase comes from the changing scale. The observable universe contains regions whose present proper distance from us grows faster than light can close that distance. This does not mean those galaxies are invisible in every case. Light received now may have been emitted long ago when the source was closer in the relevant cosmological sense, and the light has spent billions of years traveling through an expanding universe. Some photons move toward us locally throughout their journey, even while the distance to their source can grow for much of that time. That sentence is easy to rush past, but it carries much of the subtlety. A photon can always move locally at c, and yet the total distance between the emitting galaxy and the receiving galaxy can behave in ways that do not resemble a simple race. The path of light through an expanding universe is not the same as a runner crossing a fixed track. The track itself changes while the journey is happening. And at cosmic scale, the changing track becomes part of the measurement. The Hubble radius is often used as a rough boundary in this discussion, the distance at which recession speed associated with cosmic expansion equals the speed of light for a given value of the Hubble parameter. It is not a hard wall like the surface of an object. Galaxies can move across this scale in the accounting of cosmological models, and light behavior depends on the history of expansion, not only on a single present distance. The useful point is that general relativity permits recession rates beyond c without permitting local faster-than-light travel. Inflation, the proposed early rapid expansion of the universe, pushes this distinction further. In inflationary models, space expanded by an enormous factor during an extremely early interval. Regions once close enough to exchange influence could have been carried far apart by the rapid growth of space. The expansion was not a swarm of galaxies flying through pre-existing emptiness faster than light. It was a change in the scale factor of spacetime itself, described within a framework where local light speed remains unchanged. Inflation remains a model supported by several broad successes and still studied through its detailed predictions and alternatives. It helps explain features such as the large-scale uniformity of the observable universe and the origin of tiny density fluctuations that later grew into cosmic structure, yet it is not a travel method and not a loophole for sending messages. If anything, it shows how powerful the distinction is between motion through space and the evolution of space. There is a pressure-like quality to cosmic expansion when described through distance rather than machinery. No engine pushes a far galaxy away from Earth in the ordinary sense. No cable stretches between clusters. Instead, the scale of the universe changes everywhere in a way that accumulates over distance. Nearby bound systems such as galaxies, solar systems, planets, and bodies do not expand with the Hubble flow because local gravitational and electromagnetic binding dominates. Across the largest unbound separations, the growth becomes measurable. This is why the expansion of the universe cannot be used to send a ship faster than light. A galaxy receding superluminally from us is not choosing a path through local space that a spacecraft can imitate. The recession belongs to the global geometry described by cosmological coordinates. A traveler inside a local region still faces the same light speed boundary as before. Engines, clocks, signals, and matter remain governed by the local structure of space-time. Even the word speed becomes coordinate dependent in cosmology. Different choices of coordinates can describe expansion in different mathematical forms, while observables such as redshift, luminosity distance, angular diameter distance, and the cosmic microwave background provide the physical anchors. The recession speed assigned to a distant galaxy is useful inside a chosen cosmological model, but it is not the same as the speed a nearby observer would measure as the galaxy passed by. At great distances, geometry enters the word velocity. This coordinate dependence does not make expansion unreal. The redshift of distant galaxies is measured. The cosmic microwave background carries the imprint of an earlier hot, dense state. Large-scale structure records the growth of matter under gravity across cosmic time. The expansion of space is one of the central facts of modern cosmology. Its lesson for faster-than-light questions is not that relativity has failed, but that general relativity allows global distance to behave differently from local motion. The boundary around C therefore survives by becoming more precise. Nothing locally outruns a nearby light beam. No message travels from a superluminally receding galaxy to Earth faster than light through local spacetime, yet the proper distance between far-separated galaxies can increase at a rate greater than c because the metric describing the universe changes with time. The rule is local, the expansion is global. This gives one of the most important answers to the title's question. Beyond the speed of light, in cosmology, there is not necessarily a forbidden particle or a broken law. There can be a distance growing faster than light can reduce it, a horizon beyond which present signals cannot reach us if expansion continues in the required way, and a universe where the word beyond belongs to geometry rather than engines. Light still moves locally as light must. Space, under general relativity, is not required to keep distance separations changing below sea. Chapter 11. Wormholes and shortened roads. A wormhole changes the question from speed to distance. It does not begin by asking whether a traveler can force ordinary matter beyond the speed of light. It asks whether space-time can contain a path shorter than the one measured through the usual exterior geometry. If two distant regions could be joined by such a passage, then arrival might occur before light traveling by the longer outside route, even though the traveler inside the passage never locally exceeds c. The idea grew from general relativity's treatment of gravity as geometry. Once space-time could curve, bend, and form horizons, it became possible for the equations to describe shapes far stranger than the nearly flat space of daily life. The question was no longer only what objects could move through space, it was what kinds of space the equations themselves could permit. Wormholes belong to that second question. In 1935, Albert Einstein and Nathan Rosen studied a mathematical structure now called an Einstein-Rosen bridge. Their work was not a proposal for interstellar travel. It arose from attempts to understand particles, fields, and the structure of general relativity without singularities. The bridge connected two regions in the mathematical extension of a black hole solution, but it did not provide a stable, traversable tunnel for a spacecraft or signal. The connection closed too quickly and lay behind horizons that made ordinary passage impossible. That early bridge still left a durable image in the mathematics. Spacetime might contain more than one route between regions. The familiar route would run through the outside universe, across ordinary distance. Another route, if it existed and remained open, could pass through a different geometry. The traveler's local speed along that route would remain sublight. The advantage would come from the shape of the path, not from breaking the local speed rule. The distinction matters because a shortcut is not the same thing as faster local motion. A person walking through a doorway may reach the next room sooner than someone walking around a building, without walking faster. A wormhole applies a related idea to space-time, though the comparison is only a small guide. The difficulty is not the concept of a shorter route. The difficulty is whether space-time can hold such a route open in a way matter could enter, cross, and leave without encountering a horizon, a singularity, or destructive instability. The modern traversable wormhole entered physics most clearly through the work of Michael Morris and Kip Thorne in 1988, with later collaboration by Olvi Yurtsever. The problem was posed in a deliberately careful way. What would general relativity require for a wormhole that a traveler could pass through in principle? The answer was not a simple design. It was a list of physical demands, and the most important was the need for exotic stress energy to keep the throat open. A wormhole throat is the narrow region through which the shortcut passes. In ordinary gravitational systems, matter and energy curve spacetime in ways that tend to focus paths together. To keep a traversable throat from pinching off, the geometry generally requires a form of negative energy density or pressure that violates the usual energy conditions. These energy conditions are not arbitrary preferences. They are mathematical statements about the kinds of matter and energy normally observed in nature. Quantum field theory does allow small and constrained negative energy effects in certain circumstances, such as the Casimir effect between closely spaced conducting plates. That fact keeps the discussion from being dismissed as pure fantasy, yet the scale, arrangement, and stability required for a macroscopic traversable wormhole remain far beyond anything known. A tiny quantum allowance is not the same as a usable bridge between stars. Here, the geometry feels almost tactile. A passage wants to narrow, the way a stretched membrane returns toward closure when no support holds it apart. To keep it open, the supporting material would have to push against the usual tendency of gravity in an unfamiliar direction. The surface of the calculation may be smooth, but beneath it lies a demand for matter with properties that ordinary matter has not shown in bulk. Causality also follows the wormhole closely. A wormhole that connects distant regions could, under certain arrangements, become a time machine. If one mouth of the wormhole were moved relativistically or placed in a different gravitational field and then brought back, Time dilation could make the two mouths age differently. Passing through the wormhole could then connect not only different places, but different times. The problem of faster-than-light arrival returns as a problem of causal loops. This is why wormholes are never only an engineering challenge. Stabilizing the throat would be difficult enough. Preventing causality violations may be deeper. Stephen Hawking's chronology protection conjecture suggested that the laws of physics might prevent the formation of closed time-like curves, perhaps through quantum effects that become severe when a time machine is about to form. The conjecture is not a proven theorem. It is a sign of how seriously causality weighs on any geometry that appears to outrun ordinary light paths. A traversable wormhole would also have to remain gentle enough for passage. Strong tidal forces could stretch and compress objects moving through the throat. Radiation near the mouths, instabilities in the geometry, and the back reaction of matter passing through could all threaten the structure. General relativity permits many mathematical spacetimes that no material civilization could necessarily assemble or survive. The equation can describe a shape without promising a workshop for building it. Still, wormholes remain valuable because they clarify the difference between local speed and global route. A traveler entering one mouth and exiting another would not need to see a local speedometer exceed c. Locally, every small segment of the journey could obey relativity. To an outside observer comparing the arrival with a light beam sent by the ordinary exterior route, the traveler might seem to have beaten light. The apparent victory would belong to topology and geometry. Topology is the part of the story that ordinary speed language handles poorly. In a simple space, two distant points are connected by paths whose lengths differ in familiar ways. General relativity allows the geometry of spacetime to be more complicated. If the global structure includes a handle, tunnel, or bridge, then the shortest route may not resemble the straight line expectation from outside. The speed limit remains local, while the map itself has changed. No evidence shows that traversable wormholes exist. Black holes have been observed through their gravitational effects, accretion disks, stellar orbits, gravitational waves, and horizon-scale imaging. Wormholes have not. Some theoretical work explores whether certain compact objects might imitate black holes while actually being wormhole-like, but observation has not required that interpretation. The burden remains on the speculative side. The absence of evidence does not make the idea useless. In physics, impossible or unobserved structures can still teach the limits of a theory. Wormholes force general relativity to answer questions about energy conditions, topology, horizons, and causality. They also mark the place where relativity's flexibility becomes almost uncomfortable. The theory that forbids local faster-than-light motion also describes geometries where distant arrival might outpace an exterior light route if matter with unusual properties can support the shape. This is the careful meaning of a wormhole as a faster-than-light possibility. It is not a tunnel through ordinary space where a ship secretly accelerates beyond c. It is a proposed alteration in the route itself. The ship remains local, the throat remains the problem. Exotic energy remains the price in most known models. Causality remains the judge waiting beyond the calculation. Morris and Thorne's work gave science fiction a respectable mathematical doorway, but it also gave physics a list of reasons that doorway may stay closed. The paper did not show that wormholes can be built. It showed what the universe would have to supply if they were to be traversable. The requirements were severe enough to preserve the boundary even while allowing the idea to be stated. A shortened road through spacetime therefore sits between permission and refusal. General relativity permits the language. Known matter does not supply the needed support. Quantum theory allows small negative energy phenomena but constrains them sharply. Causality threatens to turn a shortcut into a loop. The result is not a practical route beyond light, but a disciplined speculation about how a universe with curved spacetime might hide distance inside geometry. The next proposal keeps the local light-speed distinction, but changes the image again. Instead of opening a throat between two regions, it places a region inside a moving pocket of spacetime. The traveler would remain almost at rest inside the pocket while space contracts ahead and expands behind. That mathematical construction is known as the Alcubierre bubble, and it shows how far general relativity can be pushed before physics begins asking what kind of matter could push back. Chapter 12. The Alcubierre bubble. Miguel Alcubierre's proposal began with a careful separation. A ship might not need to move locally faster than light if the geometry around it could be made to move in the right way. The object inside the region could remain nearly at rest with respect to its immediate surroundings, while space-time in front of the region contracted and space-time behind it expanded. In that mathematical construction, the journey would not be won by pushing the ship through space beyond c. It would be won by changing the space through which the journey was measured. The paper appeared in 1994 in Classical and Quantum Gravity. Alcubierre was working inside general relativity, not outside it, and that is what gave the idea its unusual seriousness. Special relativity forbids local faster-than-light motion for matter. General relativity, however, describes space-time itself as dynamic, capable of curvature and expansion. If the geometry could be arranged so that a bubble-like region carried a ship from one place to another, the ship's local motion inside the bubble need not violate the ordinary speed limit. This is the same distinction that made cosmic expansion important, but now placed into a proposed engineered shape. In cosmology, distant galaxies can recede superluminally because the scale of space between them changes. In the Alcubierre metric, the change is concentrated around a moving region. Space contracts ahead, expands behind, and the interior rides between those gradients. The ship is not supposed to chase a light beam through nearby space. The bubble's geometry changes the bookkeeping of distance. The word bubble can make the idea sound softer than it is. In the mathematics, it is not a soap film or a transparent shell. It is a region of space-time described by a metric, a rule for measuring intervals, distances, and times. Inside the bubble, space-time can be arranged to remain relatively flat, so that a traveler would not necessarily feel enormous acceleration. Around the bubble wall, however, the geometry changes sharply, and that wall carries the burden of the whole construction. A gradient surrounds the imagined pocket. Ahead of it, distances are compressed in the chosen direction. Behind it, distances are stretched. The interior stays calm only because the strain has been placed elsewhere in the geometry. The calculation has a smooth center and a demanding edge. To describe the ship as moving would be less exact than describing the surrounding space-time as being sculpted into motion. That sculpting requires stress energy. In general relativity, geometry is not free. Curvature is related to matter, energy, pressure, and momentum through Einstein's field equations. Once Alcubierre wrote down the desired geometry, the equations could be read in the other direction, asking what kind of stress energy would be needed to create it. The answer was severe. The original warp drive metric required negative energy density in ways that ordinary matter does not provide. Negative energy is not the same as having no energy. It means that, relative to a chosen reference, the energy density in a region is below the vacuum baseline expected in ordinary conditions. Quantum field theory allows limited negative energy effects in special arrangements, such as the Casimir effect between closely spaced conducting plates. Yet these effects are small, constrained, and not available as a reservoir for shaping a macroscopic warp bubble around a spacecraft. This is where the proposal changes from a seductive geometry into a hard physical question. General relativity can allow a metric to be written down, but the universe must still supply the material content that produces it. A bridge drawn on a map is not a bridge made of steel. A space-time metric is not automatically a machine. The Alcubierre bubble shows that a superluminal-looking route can be expressed mathematically, while also showing that the matter required by that expression may not exist in usable form. Early estimates of the energy requirement were enormous. Later work explored modifications that reduced the apparent amount, including Chris van den Broek's 1999 adjustment, which changed the geometry so that the external size of the bubble could be small while the interior volume remained larger. Such proposals made the numbers less hopeless in some formulations, but they did not remove the deeper need for exotic stress energy or the problems of stability and control. Reducing an impossible demand is not the same as making it physical. The distinction between mathematical existence and physical construction is especially important here. General relativity contains many exact or approximate solutions that are useful even when they do not describe objects anyone expects to build. Some reveal what the equations permit under idealized conditions. Some expose the limits of energy conditions. Some act as test cases for deeper theories. The Alcubierre metric belongs to this family. It is a serious object of calculation, not a blueprint folded inside a laboratory drawer. A traveler inside the bubble would also face a communication problem. If the bubble moved effectively faster than light relative to the outside destination, parts of its leading edge could lie outside the causal reach of the ship inside. The traveler might not be able to control the front of the bubble from within it. A vehicle that cannot send instructions to the geometry carrying it has a problem unlike ordinary navigation. Steering becomes a question about horizons, not only about engines. The same issue returns in another form when the bubble is created or stopped. If the geometry must already exist ahead of the ship in order to move superluminally, then forming it from the ship's own location may require influence to reach regions that are not causally accessible. The metric can describe a bubble in motion, but creating that bubble from ordinary initial conditions is a separate problem. A path written into space-time is not automatically a path that can be summoned by equipment inside the path. Quantum effects add further unease. Later analyses have suggested that warp-drive spacetimes may suffer from instabilities or severe radiation near horizons, depending on the model. Quantum fields do not always remain passive when spacetime geometry is arranged into extreme forms. Where horizons appear, particle creation and energy buildup can become important. The same mathematics that permits a shape can also reveal why the shape may not remain gentle. The physical picture therefore narrows. A warp bubble is not a ship with a faster engine. It is a proposed space-time configuration requiring exotic energy, careful geometry, causal access to the bubble wall, and stability against quantum effects. Each requirement is difficult alone. Together, they make the idea speculative in the strict sense, allowed as a mathematical exploration, not established as a possible technology. Yet the Alcubierre proposal remains valuable because it forces the light-speed boundary to be stated more precisely. Special relativity does not say that all distances between all objects must change at rates below c in every coordinate description. It says that local motion through space-time is bounded for matter and information. General relativity allows space-time geometry itself to be arranged, at least in equations, in ways that can make distant arrival appear faster than an exterior light beam. The local rule survives by moving the burden onto geometry. That burden is heavy. The bubble wall must carry the distortion. The required stress energy must violate familiar conditions. The causal structure may prevent internal control. Radiation and instability may appear where the geometry becomes extreme. The ship inside, often imagined as the center of the story, is almost the least active part of the proposal. The real subject is the surrounding space-time and the cost of shaping it. In this way, the Alcubierre bubble sits beside the wormhole without being the same thing. A wormhole shortens the route by connecting regions through a throat. A warp bubble keeps the route external but changes the geometry around the traveler. Both try to preserve local sublight motion. Both require forms of matter or energy beyond ordinary engineering. Both threaten to entangle faster arrival with causality. The resemblance is not in their shape, but in the way they move the problem away from engines and into space-time itself. No observation suggests that natural Alcubierre bubbles exist. No experiment has produced a warp field. No known material supplies the required negative energy in macroscopic, controllable amounts. The proposal stands as a mathematical question addressed to general relativity. If the geometry is written this way, what must the universe provide and what consequences follow? The answer, so far, is that the universe would have to provide far more than a clever propulsion system. For the question of what happens beyond light speed, this matters. Beyond c, when handled through warp geometry, there may be no local crossing at all. There may instead be a region where ordinary local speed remains below the limit, while the global arrangement produces faster arrival. But that sentence does not make the journey easy. It only relocates the impossibility. The obstacle is no longer pushing the ship past light. It is persuading space-time to take a shape that known matter does not know how to hold. The Alcubierre bubble therefore leaves the boundary intact, but less naive. It shows that relativity is not a simple fence around imagination. It is a set of rules that can distinguish local motion from global geometry, speed from path, and a metric from a machine. The speculative doorway remains open on paper, but the paper is covered with conditions: negative energy, horizon behavior, quantum stability, and the old demand that causes remain before their effects. The next difficulty gathers around those horizons. If a bubble moves in a way that outpaces light relative to the outside, the geometry around it may form regions that cannot communicate with the ship inside. A traveler may be carried by a pocket of space-time while losing the ability to command parts of that pocket. At that point, the faster-than-light question becomes less like propulsion and more like being enclosed inside the causal structure one has tried to use. Chapter 13. Horizons around a moving pocket. A moving pocket of space-time carries its own boundary problems. In the simpler picture, a warp bubble seems almost gentle: a quiet interior, a shaped wall, a contraction ahead, an expansion behind. The ship inside does not locally outrun light. The surrounding geometry performs the unusual work. Yet once the bubble is allowed to move effectively faster than light relative to distant outside observers, the geometry begins to develop regions that cannot all speak to one another. This is where horizons enter. A horizon is not always a black hole surface, though black holes provide the most familiar example. More generally, a horizon marks a causal boundary, a division between regions that can exchange signals and regions that cannot. Light cones still exist near every event, but the global geometry can tilt and arrange them so that some paths are cut off from others. A signal may travel perfectly at light speed and still be unable to reach a particular region. For a warp bubble, this becomes a practical difficulty before it becomes a philosophical one. If the front part of the bubble lies outside the causal reach of the ship inside, then the traveler cannot send an ordinary command to that front wall. The very geometry that allows faster arrival may prevent the occupants from controlling the geometry that carries them. Steering, slowing, shaping, and stopping become questions about causal access, not merely about power. The problem can be stated without drama. A ship inside a superluminal bubble may be locally safe in the central region, but if the forward edge is causally disconnected, the ship cannot direct that edge from within. The bubble would have to be arranged in advance, or controlled from outside, or governed by a mechanism not contained in the simple metric itself. A drive that must be prepared ahead of its own journey is not a drive in the ordinary sense. This is one reason the Alcubierre idea remains more like a space-time specimen than a vehicle. The metric describes a geometry that can be analyzed. It does not automatically describe how that geometry is created, how it begins from ordinary initial conditions, how it responds to disturbances, or how a traveler adjusts its course. General relativity can give the shape. Physics must still ask how the shape is made to exist. A causal boundary has a strange texture in thought. It is not a wall made of material, and there is no surface on which a hand could rest. Yet it has a firmness that ordinary matter cannot ignore. Signals approach it according to their allowed paths, and the geometry decides whether those paths continue into the needed region. The limit is written into direction and time rather than into substance. Black hole horizons offer the clearest comparison, though a warp horizon is not the same object. Around a black hole, the event horizon marks the boundary beyond which future directed paths remain inside. Nothing locally exceeds light speed at the horizon. The confinement comes from the way space-time is arranged. In warp bubble discussions, horizon-like features can appear because the effective superluminal motion of the bubble changes which regions can influence which other regions. Those horizon-like structures create several linked concerns. One is control. Another is stability, A third is quantum behavior near the boundary. Classical general relativity can describe a space-time geometry, but quantum fields living on that geometry may not remain quiet when horizons are present. In black hole physics, horizon structure leads to Hawking radiation. In warp drive analyses, similar questions arise about whether quantum effects would build up near bubble horizons or destabilize the configuration. The details depend on the model, and this is important. Not every calculation gives the same severity in the same form, because different warp geometries, assumptions, and quantum field treatments lead to different results. Still, the pattern is consistent enough to matter. Extreme space-time arrangements invite quantum back reaction. The geometry cannot be treated as a silent stage if the fields moving through it begin to alter the conditions that support the stage. A superluminal bubble may also collect radiation in uncomfortable ways. Light, particles, and background fields encountered along the path could interact with the bubble geometry. Some analyses suggest that energy could accumulate at the front edge, or that radiation released when the bubble stops might become severe for anything near the destination. The image of smooth travel hides the fact that a moving space-time distortion must still meet the contents of the universe through which it passes. There is also the question of the bubble wall itself. A thin wall makes the geometry sharper and may reduce some volume requirements, but sharp gradients often increase stress energy demands. A thicker wall spreads the distortion, but changes the scale of the configuration. The shape function chosen in the metric is not a cosmetic detail. It determines how rapidly space changes from the calm interior to the exterior region, and that transition is where much of the physical cost appears. Inside the bubble, the traveler may feel little acceleration in the idealized model. That calm center can mislead the imagination. The dangerous physics has not disappeared. It has been moved outward. The bubble wall carries the gradients, the exotic stress energy, the causal boundaries, and the possible quantum instabilities. A quiet cabin at the center of a calculation does not make the surrounding space-time gentle. This relocation of difficulty has appeared before. In near-light acceleration, the obstacle moved from engine strength into relativistic energy. In wormholes, it moved from local speed into exotic matter and throat stability. In warp travel, it moves into the wall, the horizon, and the global causal structure. Each speculative route tries to avoid one form of the light speed limit, and each meets the same deeper demand in another form. A moving pocket also raises the issue of initial data. In general relativity, a spacetime is not only a finished picture, it must be connected to possible initial conditions, a state of the universe at one time, evolving under the field equations into later states. A metric that describes a warp bubble already in motion may not show whether ordinary matter and fields could produce that bubble from an initial state without violating constraints. The existence of a written solution is therefore only the beginning of the question. Some work has tried to soften the demands of warp geometry by changing the metric, altering the bubble shape, reducing the required energy, or exploring subluminal versions of warp-like motion. These efforts are useful because they separate which problems come from superluminal behavior and which come from the more general idea of shaped spacetime. A subluminal warp configuration would not give faster-than-light arrival, but it may still teach how general relativity responds to engineered geometry. The moment the bubble becomes superluminal, however, causality returns with greater force. A path that effectively beats light across an exterior distance risks the same causal tensions that haunted tachyons and wormholes. If two observers in relative motion can arrange superluminal connections in different directions, closed causal loops may appear. The warp bubble may avoid local violation, but the global arrival can still disturb the ordering of events unless additional restrictions prevent it. This is why faster-than-light ideas tend to gather horizons around themselves, not always literal event horizons in the black hole sense, and not always in the same mathematical form, but boundaries of influence, control, and consistency. The universe may allow equations that look like shortcuts or moving pockets, while surrounding them with conditions that keep ordinary causality from being easily overturned. The boundary around light speed does not always stand at the front door. Sometimes it waits inside the structure of the proposed escape. There is a modest lesson in the control problem. A vehicle is useful only if its motion can be commanded from where the travelers are. If the fastest version of a warp bubble places part of its own operating surface beyond internal command, then the ship is less like an engine and more like a region carried by a prearranged space-time event. The traveler becomes cargo inside geometry rather than pilot of a machine. For now, that is where the Alcubierre-style proposal remains. It is a valuable mathematical construction, a way to test how general relativity distinguishes local motion from global geometry. It has not become a physical mechanism. Negative energy remains unresolved, horizon behavior remains difficult, quantum stability remains uncertain, and the creation of the bubble from ordinary conditions remains outside demonstrated physics. The idea survives as a boundary study. A horizon around a moving pocket therefore answers the faster-than-light question with restraint. Beyond light speed, if space-time geometry is forced into extreme forms, control itself may become separated from motion. The ship may not break the local speed rule, but the geometry that carries it may place its own edges beyond reach. The attempt to outrun light through space-time can end by revealing how carefully space-time guards the order of signals. After these speculative paths, the final question becomes quieter. Physics has allowed mathematics to approach the boundary from many sides: particles that would live above sea, measurements that seem to arrive too soon, patterns that move without carrying messages, entangled systems that correlate without communication, distances that grow through expansion, and geometries that shorten or reshape paths. What remains is not a single door beyond light, but a set of limits, openings, and unfinished theories arranged around one stubborn local rule. Chapter 14. What physics leaves open. After all the apparent doors have been examined, the boundary remains local. Massive matter still does not accelerate through light speed. A signal still does not carry chosen information outside the light cone. A particle seen in an equation is not automatically a particle found in nature. A geometry written inside general relativity is not automatically a machine. The speed of light survives not because every question is closed, but because every serious question has to pass through the same narrow test. What moves, what carries information, and what causal order remains? This is the quiet shape of the answer. Beyond light speed, there is no single region where physics simply changes its mind. There are different meanings of beyond. A tachyon would belong to one kind of beyond, if such particles existed as real faster-than-light objects. A shadow sweeping across a distant surface belongs to another, where no substance or message travels along the sweep. A galaxy receding superluminally through cosmic expansion belongs to another still, where the distance grows through space-time geometry rather than local motion. The phrase sounds singular, but the physics divides it into separate claims. Established relativity gives the firmest part of the answer. In local space-time, any massive object remains below c. It may approach the limit with enormous energy. Its clock may accumulate less time along a high-speed path. Its measured length may contract along the direction of motion, yet it remains on a time-like world line. Light and other massless influences follow null paths. Faster-than-light paths, if treated as ordinary signal paths, become space-like, and space-like connection unsettles the shared ordering of cause and effect. Precision experiments have pressed on this structure for more than a century. Michelson and Morley found no ether wind. Particle accelerators operate only because relativistic momentum and energy are treated correctly. Muons reaching Earth's surface carry time dilation into natural observation. Atomic clocks in aircraft and satellites require relativistic accounting. Neutrino timing experiments, including the Opera anomaly and its correction, show how carefully any claimed excess must be handled. The boundary is not held by one experiment alone. It is held by a network of measurements. Lorentz invariance is one name for part of that network. It means, in practical terms, that the laws of physics preserve the same relativistic form when seen from different inertial frames. Modern tests look for tiny violations of this symmetry in particle behavior, atomic clocks, light from distant astrophysical sources, and high-energy events. Any confirmed deviation would matter. So far, the evidence has placed extremely tight limits on such violations, leaving ordinary special relativity intact across a wide range of scales. This does not make physicists stop asking. A theory can be strong and still incomplete. Special relativity and general relativity do not yet sit comfortably with quantum mechanics in every regime. The deepest problem appears where gravity, quantum fields, and extreme spacetime structure meet, near black hole interiors, at the earliest moments of cosmic history, and perhaps at distances so small that the smooth geometry of spacetime may no longer be the final description. The light-speed boundary may be explained more deeply in a future theory, even if that future theory does not remove it. Quantum gravity is the name given to that unfinished territory, though the name covers many approaches: string theory, loop quantum gravity, causal set ideas, asymptotic safety, emergent spacetime proposals, and other frameworks all try in different ways to understand how gravity and quantum physics belong together. Some preserve Lorentz symmetry exactly. Some allow possible tiny deviations under special conditions. Some suggest that spacetime itself may not be fundamental in the way ordinary relativity assumes. None has yet replaced the established light-speed boundary in tested local physics. This is where speculation should remain careful. Future physics might change the meaning of spacetime. It might show why Lorentz symmetry appears so exact. It might reveal that causality, locality, and geometry emerge from a deeper structure not yet experimentally accessible. But it would still have to explain why photons, particles, clocks, accelerators, satellites, gravitational waves, and astronomical observations behave as they do now. A deeper theory cannot simply discard a successful boundary. It must contain the old success inside a wider account. There is a difference between an open question and an unlocked door. The nature of spacetime at the Planck scale is open. The final relationship between quantum mechanics and gravity is open. The deepest reason for the light speed limit may be open. Usable faster-than-light communication is not open in the same way within known physics. It has no experimental support, and it carries causal difficulties that any future theory would have to solve rather than ignore. The Planck scale often appears in these discussions because it marks a region where ordinary expectations may fail. The Planck length is about 1.6 times 10 to the minus 35 meters, far smaller than anything directly probed by present experiments. At such scales, some approaches suggest that spacetime might have a discrete, foamy, or emergent character. These words are imperfect, and each belongs to a different theoretical tradition. What matters here is that the smooth spacetime of relativity may not be the final material out of which physical description is made. If spacetime is emergent, then light speed may also have a deeper origin. It could be a limiting speed arising from the large-scale structure of the underlying theory, much as sound speed arises from the properties of matter without being fundamental to empty space. That comparison has limits, because light speed is far more deeply woven into known physics than sound speed is. Still, the possibility shows how future theory might explain the boundary rather than merely assume it. A deeper explanation would not automatically make superluminal travel available. In many systems, emergent limits remain powerful within the regime where the system exists. A wave in a material cannot exceed the material's own rules simply because the material has an underlying atomic structure. In the same way, if spacetime has a deeper substrate, ordinary matter and information may remain bound by the effective light cone that emerges at accessible scales. The foundation may change without turning every limit into an engineering option. Causality is likely to remain the hardest guardian. Faster-than-light communication is dangerous not because physicists dislike the idea, but because it can scramble the order of events in relativity. If a future theory permits anything that looks superluminal, it must either protect causal order by some new mechanism, or replace the old notion of causality with one that reproduces ordinary cause and effect where experiments already confirm it. No successful theory can allow contradictions to appear in the laboratory while claiming only to be more advanced. This is why Hawking's chronology protection conjecture still haunts discussions of wormholes and warp geometries. It is not proven, and it may not be the final word, but it names a suspicion that the laws of physics resist the formation of time machines. Quantum effects near would-be closed time-like curves might grow in ways that prevent the dangerous geometry from forming, or some deeper law may remove such paths before they become physical. The details remain unsettled, but the demand is clear. Causality must be accounted for. Astrophysics also keeps pressure on speculative freedom. Light from distant gamma-ray bursts, high-energy cosmic rays, neutrino observations, gravitational wave detections, and precision timing from pulsars all test how signals move across enormous distances. Tiny deviations from light-speed behavior can accumulate over cosmic baselines. This makes the universe itself a long instrument. A slight difference too small for a laboratory might become visible after billions of years of travel. Gravitational waves gave one of the cleanest modern confirmations of this shared speed. In 2017, the gravitational wave event GW 1170817, produced by a neutron star merger, was followed by electromagnetic radiation from the same event. The gravitational waves and light arrived close together after traveling across roughly 130 million light-years. The comparison placed very tight constraints on any difference between the speed of gravity and the speed of light. General relativity's causal structure passed another difficult test. Such measurements do not close every speculative question. They narrow the space in which answers can live. A theory that changes the light speed boundary must pass through all the places where that boundary has already been measured: in accelerators, in clocks, in astrophysical timing, in quantum experiments, in satellite systems, and in gravitational wave astronomy. The old theory has left its fingerprints across too many instruments for a new one to erase them casually. For a civilization hoping to cross interstellar distances, this may feel severe. The stars are far, and light itself takes years to move between even the nearest ones. Proxima Centauri lies more than 4 light-years away. The center of the Milky Way lies tens of thousands of light-years away. Other galaxies place distance into scales where ordinary travel becomes almost meaningless. It is understandable that imagination searches for routes around C, because C is fast and still too slow for human longing. Physics does not answer longing directly. It gives permitted motions, measured speeds, causal structures, and mathematical possibilities. It allows near-light travel in principle for massive objects with impossible practical costs, but not crossing by acceleration. It allows time dilation, but not free movement into the past. It allows cosmic expansion to separate galaxies faster than light, but not a local engine that imitates that recession. It allows wormhole and warp metrics on paper, while surrounding them with exotic matter, horizons, and instability. So what really happens beyond the speed of light depends on which boundary is being approached. For matter, the boundary becomes an energy demand without finite completion. For clocks, it becomes time dilation along different paths. For signals, it becomes the edge of causal influence. For wave patterns, it becomes a lesson in distinguishing appearance from information. For entanglement, it becomes correlation without messaging. For cosmology, it becomes the growth of distance. For speculative geometry, it becomes a question about what space-time can be made to do and at what cost. The most honest answer is therefore not a simple yes or no. It is a layered answer. Known local physics says no to massive matter and usable signals crossing C. Known experiments support that refusal with great precision. General relativity opens mathematical structures where arrival can appear faster than exterior light, but known matter does not provide the required conditions in any practical form. Quantum mechanics gives non-classical correlations, but not faster messages. Cosmology gives superluminal recession, but not local violation. Beyond that layered answer, physics leaves room for deeper explanation. Perhaps a future theory will show why C has the value and role it has. Perhaps space-time will be understood as emergent from something that does not resemble distance and duration at all. Perhaps causality will be seen as a large-scale ordering arising from smaller rules still unknown. Those possibilities do not hand over a warp drive or a tachyon radio. They leave the boundary available for explanation, not for casual removal. The speed of light therefore remains both limit and clue. It limits local matter, energy transfer, and communication. It clues physicists toward the structure beneath space and time. A mere speed would not do so much work. This one does. It appears in electromagnetism, relativity, quantum field theory, gravitational waves, cosmology, and the definitions by which measurement itself is made precise. At the end of the inquiry, light has not been defeated by speculation. It has been clarified by it. Each proposed exception forces a more careful sentence. Faster than light compared with what? Moving through space or changing space, carrying information or only displaying a pattern, crossing a local boundary or shortening a global path, existing as matter or appearing as a sign of instability in an equation. The question becomes smaller in some places and larger in others. What remains is a universe with strict local rules and wide mathematical imagination. The rules keep signals ordered, clocks accountable, and matter below the boundary. The imagination explores geometries, fields, horizons, and structures that may never become machines. Between them lies the frontier where physics often lives, not in the promise that anything can happen, but in the careful discovery of why only some things do. The final movement now returns from that frontier to the measured world. Ordinary clocks continue to count. Signals continue to widen outward at finite speed. Matter continues to move along paths that remain below C. Whether in a laboratory beam, a satellite orbit, a cosmic ray shower, or a quiet instrument waiting for the next test, the boundary is still there, not as a wall in space, but as a condition inside the way space and time hold together. A photon crosses a vacuum according to the same constant that began this story. A clock beside an experiment records its own proper time. A detector waits for the arrival of a particle, a pulse, or a wave from some distant event. The signal comes when its path allows it to come, neither early enough to break cause nor late enough to erase the order that carried it. And below that order, ordinary matter remains where relativity placed it, always able to approach the speed of light, never able to pass through it by motion alone. The journey is complete. Rest well.